which is nearly 30 kg of carbon dioxide. %80 of carbon dioxide emissions worldwide are caused by the energy sector, and 35 billion tons of carbon dioxide are recently emitted annually, nearly 30 kg of carbon dioxide per capita per day. The average temperature of the Earth should be kept within 2 degrees Celsius by the next decade. And to accomplish this 2 degrees Celsius goal, a quick and radical fall in carbon dioxide emission is essential, achieving a net zero carbon dioxide emission by the year 2050. The circular economy concept has achieved great attention worldwide in the recent decade. The current linear economy practice of take, make, use, and dispose pushes our society's requirements beyond the Earth's capacities. However, the circular economy is based on 3 principles. Number 1, design out waste and pollution. And number 2, keep the products and materials in use and regenerate the biological system. Hydrogen can be considered a revolutionary energy carrier that can undoubtedly have a significant and persuasive influence on the global energy transition. Because of its high level of calorific value, energy per unit mass compared to all other fuels, high level of thermal gradient with greater energy density, low molecular mass, and the energy requirement to detonate an air hydrogen. It is estimated that the global hydrogen demand increased 3 times from 1975 to 2018. The pure hydrogen demand is 70 million tons per day. An additional 45 million tons is used as a mixture of different gases. By 2050, the global hydrogen demand will be 3.3 gigaton per year. However, 97% of total hydrogen now comes from fossil fuels, and only 0.7% of total hydrogen comes from the renewables. The water industry provides various socio-economic facilities by supplying potable water, wastewater services in the economy's industrial, domestic, and business-related sectors. However, the identification and potential implications of circular economy in water industry are essential for sustainable water resource management and resource recovery. As we can see, aeration is considered the largest energy consumer, requiring 40 to 60% of the total energy demand of a typical wastewater treatment plant. Thus, water industry can be a good source of simultaneous hydrogen and oxygen production by developing some novel processes. The hydrogen can be used in different sectors like power generation, heating and house, industrial applications, renewable electricity, zero-emission transport, and ammonia fertilizers. Further, the oxygen can be recycled to the biological wastewater treatment plant to reduce the overall energy consumption, and thus we can make a self-energy generating water industry incorporating the circular economy. Based on the different feed sources, hydrogen production technologies can be divided into major 2 groups: hydrogen production from pure water and hydrogen production from wastewater. In our previous study, we made a detailed techno-economic and environmental feasibility of hydrogen production technologies, where we ranked proton exchange membrane and dark fermentation are the best hydrogen production technologies based on cost, energy efficiency, exergy efficiency, global warming potential, global acidification potential, and social cost of carbon. However, most of the commercial hydrogen production technologies, such as proton exchange membrane, alkaline exchange membrane water electrolysis, and anion exchange membrane electrolysis, are pure water intensive. It was estimated that 1 kg of hydrogen production needs almost 60 to 95 liters of good quality raw water. Moreover, The catalyst and membrane materials are expensive, which ultimately increase the hydrogen production cost. On the other hand, the dark fermentation process is limited by the activity of microorganisms, and this process also emits greenhouse gases in the environment. Over the last 60 years, electrodialysis is considered as one of the most suitable technology for desalination because it has higher water recovery rates compared to reverse osmosis. However, there has been a minimal research conducted related to the reuse of the elemental gases produced in the electrodialysis system. And these gases are flow freely into the atmosphere. As a gas collection strategy, during ED treatment is not included yet. The hydrogen produced during the ED process produces electrical energy and reduces the energy cost of desalinations. And the oxygen produced can be recycled and used in the biological wastewater treatment system. This figure represents a proof of concept of hydrogen and oxygen production at the anode and cathode end by electrodialysis techniques. However, this study showed the low purity of hydrogen production. The bipolar membranes are special class of ion exchange membranes constituted by a cation and anion exchange layer, allowing the generation of protons and hydroxide ions via a water dissociation mechanism. The BPM-assisted process that has recently gained attention is water electrolysis for hydrogen production via bipolar membrane electrodialysis. BPM-assisted electrolysis can be a promising alternative to produce hydrogen by using wastewater streams. However, the process efficiency is still relatively low in this technology as well. Gel polymer electrolytes are materials which are neither solid nor liquid, but hold both the cohesive properties of solids and the diffusive character of liquids. Hence, these electrolytes have become relevant due to their use as excellent substitute of the liquid electrolytes. GPS can be prepared by trapping liquid electrolytes into different polymer hosts. However, PBA doped with potassium hydroxide has been studied extensively and received much attention due to its wide application in fuel cell. In addition, with the aim to improve their electrochemical and mechanical properties, PBA has been blended with other materials such as polymers and cross-linking agents like melamine foam. Currently, there exists a significant number of green hydrogen production technologies based on scaling up issues. Optimal production and process optimization could be one of the most sustainable scaling up issues of green hydrogen productions. However, machine learning based prediction and optimization of green hydrogen production technologies from water industry for a circular economy could be a plausible solution for these scaling up issues. We identified 3 research gaps during our literature review. The research gap 1 include the existing hydrogen production technologies are mostly pure water intensive, which lacks circularity of other resources such as oxygen. And the hydrogen production technologies in wastewater are still in their preliminary stages, which also lacks the integration between water industry and circular economy. The research gap 2 highlights the expensive membrane materials, high cost of catalyst, low energy efficiency, and also high catalyst loading. And the research gap 3 illustrates the major challenge for developing a future hydrogen economy is scaling up issue of hydrogen production, and also the prediction and optimization of hydrogen production process parameters. And additionally, matching supply and demand uncertainty is a significant hurdle for future hydrogen production. However, based on the 3 research gaps, we have targeted 3 objectives. Objective 1 is the development of novel, sustainable, and novel hydrogen production process. Objective 2 include the development of novel membrane materials, and the last objective is modeling and machine learning to study hydrogen production process optimization. And to accomplish these 3 objectives, I am planning to execute 5 projects during my PhD studies. My project 1 is urine electrolysis for simultaneous hydrogen production and urine concentration. Nutrient recovery from human urine has emerged as a prominent area of research interest, which started a transition from linear economy to a circular economy in nutrients, where urine recycling can be considered as a viable fertilizers. However, membrane bioreactor has proven to be highly effective liquid fertilizer, retrieving all major nutrients like nitrogen, potassium, and phosphorus. But MBR is highly energy intensive. Thus, development of novel process for simultaneous liquid fertilizer, hydrogen, and oxygen production via urine electrolysis is urgently needed. The key objective of this investigation is to establish a circular economy-based self-energy generating urine management in terms of the development of a future hydrogen as well as oxygen economy. The urine electrolysis system incorporates a hydrophobic membrane that functions like membrane distillations, which only allows the water vapor across the membrane to concentrate urine and generate hydrogen utilizing the PbA-QH hydrogel as an electrolyte. During the process, water within the urine is vaporized as it passes through the MD membrane, while the concentrated urine is returned to the feed tank. The water vapor condenses into PbA-QH hydrogel compartment, where the hydroxide anions reduce to oxygen gas at the electrolyte catalyst interface, and water oxidizes to produce hydrogen gas at the electrolyte and electrode interface. This slide shows the materials we used in the urine electrolysis system. The PbA-QH hydrogel was prepared by dissolving 5% of PbA in DI water. And the membrane electrode assembly was prepared by gas diffusion electrode techniques. The cell test was conducted by comparing with the feed sources of DI water and MBR treated urine. The feed temperature was maintained by 35 degrees Celsius to mitigate the volatile ammonia transport through MD membrane from the feed urine. The effective surface area of the membrane was 6.75 centimeters, and the feed flow rate was 200 ml per minute, and the initial feed pH was 6.2, and a calibrator pump was used to measure the concentration of oxygen and hydrogen in the system. The urine concentration and long-term cell test was done by fixing the voltage at 2 volt, and the urine was concentrated for 96 hours, and the concentration level was monitored at the 24 hours of intervals. From these tables, it was observed that the hydrogel composed of melamine PbA-QH at a concentration of 28% exhibited the highest ion conductivity of 173 millisiemens per centimeters. The decreasing concentration of QH solution led to higher ion conductivity, indicating their lower resistance. The PbA-QH hydrogel fabricated without melamine demonstrated a conductivity of only 79 millisiemens per centimeter, which was approximately 2 times lower compared to the hydrogel prepared with melamine. The incorporation of melamine into the PbA-QH hydrogel leads to a reduction in electrical resistance due to the minimized volume contraction of the hydrogel. The cell test results was performed using DI water and ambient treated urine as a feed source for comparative analysis. From figure A, we can see that basically all melamine PBA KOH hydrogel showed a continuous increase in current density when the voltage increased. However, melamine PBA KOH 38% hydrogel exhibited the most excellent data, achieving a current density of 212 milliampere per centimeter square for DI water and 204 milliampere per centimeter square for the ambient treated urine. But it was expected that the melamine PBA KOH 28% hydrogel would exhibit the most superior performance because it had the highest ion conductivity. The observed trend can be primarily attributed to the design of the water electrolysis system. Because the MD membrane is in direct contact with the feed urine, allowing continuous transport of water vapor to the hydrogel electrolyte. This process temporarily dilutes the concentration of KOH in the hydrogel and promotes swelling of the hydrogel electrolyte, which stimulates an increase in ion conductivity and reduce ion mobility resistance. Moreover, the rate of hydrogen during cell test was 32.48 milliliter per minute, whereas the rate of oxygen production was 21.23 milliliter per minute. To accurately ascertain this, the current density of melamine PBA KOH 38% was measured for 800 minutes at 2 volt. It can be observed that both feed waters show a decrease in current density until 200 minutes. After 200 minutes, the current density of DI water reaches a stable state, whereas the current density for the ambient treated urine progressively decreases over time. This behavior can be predominantly attributed to fouling phenomenon taking place in MD membrane, leading to a reduction in water vapor transportation. The composition analysis of concentrated urine over 96 hours shows that over a period of 96 hours, the initial 500 gram of feed urine was reduced to 99.6 gram, achieving a maximum concentration factor of 5, which is approximately 80%. The initial ammonia, nitrogen, and nitrate nitrogen were concentrated up to 9,000 and 8,000 milligram per liter, respectively. Other ions such as the phosphate, potassium, sulfate, magnesium, chloride, sodium were also effectively rejected by the MD membrane, indicating their successful retention during the process without any membrane wetting. A previous study has demonstrated the effectiveness of this urine-derived fertilizer, showing comparable results in plant growth to commercial fertilizers. Consequently, the resulting 5-fold concentrated urine after 96 hours of operation exhibits significant potential as a liquid nitrogen, phosphorus, and potassium fertilizers. The system successfully produced a total of 99.91 liter of hydrogen and 65.31 liter of oxygen during the 96-hour operation of the electrolysis system. This slide shows the membrane foulings of the MD membranes. The SEM analysis clearly exhibited the presence of organic impurities and other contaminants adhering to the surface of the foul PTFE membrane when compared to the pristine or virgin PTFE membrane. The EDS results reveal the detection of oxygen, chloride, phosphorus, sulfate, sodium, magnesium, and calcium. On the contrary, only carbon and fluoride elements were found in the virgin PTFE membrane. The FTIR data revealed a presence of amino bending peak and sulfoxide stretching peaks. However, the virgin PTFE membrane displayed a contact angle of 142 degrees, while the foul PTFE membrane showed a reduced contact angle of 66 degrees, indicating a significant increase of hydrophilicity due to the membrane fouling. Actually, this project was my first target, but my BPMED reactor was broken recently. That's why I didn't complete or get some preliminary results for these experiments, but I already made the setup, which I will be conducted in Korea in the next month. So my project 2 is bipolar membrane electrodialysis techniques for simultaneous resource recovery and hydrogen production from human urine, which will be a proof of concept, basically. This slide shows the schematic of the BPMED systems. The BPMED cell setup was a 5-compartment acrylic XT cells. The 2 electrode compartments were separated from the 3 other compartments by 2 bipolar membranes. These 2 bipolar membranes. The first concentrated compartment, this one, was separated from the urine compartment with an anion exchange membrane. The urine compartment, the middle one, was separated from the second concentrated compartment by a cation exchange membrane. The effective membrane surface area for each chamber was 15 centimeter, and the volume of each chamber was 30 ml. Membrane bioreactor treated urine will be used as a feed source for these experiments, and 0.1 molar sodium nitrate will be used as an electrolyte in the both anode and cathode compartment. The hydrogen and oxygen produced at the cathode and anode end will be collected by a Tedlar gas sampling bag for GCT-CD analysis. The materials which I will be used in the BPMED experiments are listed here. And this slide shows the BPMED reactor. Currently, unfortunately, this reactor has been broken by someone in the lab, and the cell setup, my cell setup. My future experiments I'm planning to complete are in these experiments are the primary matrix characterization, which can be brine, effluent from secondary clarifier, or MBR permeate, and the pH and EC of the feed solution before and after BPMED experiments, and the effects of electrolyte on hydrogen production. The matrix will be characterized after BPMED test as well, and the hydrogen and oxygen gas volume data, hydrogen and oxygen purity data, cell voltage during BPMED experiment with time, and the electrical energy requirements in the BPMED process to finalize a techno-economics of this process, and the energy saving using a fuel cell. And finally, the application of oxygen in the MBR aeration. My future research plans and time frame. So I'm planning to complete 5 experiments during my PhD studies, and my probable thesis completion time is February 2026. This is the list of my UTS publications as a first author. And this slide shows my completion of research data management plan, research project safety plan, and two mandatory courses, where one of the courses I got high distinction. Thanks for your listening.